Hello, Theoretical Chemistry. Welcome back to another day. Today we're going to be continuing to talk about these different compounds and in particular another tool for analyzing them. Now up until this point we've just been looking at compounds. How do you name an acid? How do you name ionic? How do you name a molecule? How do you name a hydrocarbon? How do you compare the amount of oxygen to carbon, the percent of hydrogen to sulfur? We've been analyzing, and our most recent tool has allowed us to go from the elements in a compound to the percent. Today, we're going to flip it. We're going to say if we were given the amounts of each element in our compound, could we go backwards to the original compound? So that's the goal. That's the plan. And we give that a name. Before we really get into that, let's play a little let's play a little Mr. Rogers. Now, one of these things is not like the others. One of these things just does not belong. One of these things is not like the others. One of these things just doesn't belong. Can you tell which one is not like the others by the time I finish this song? I'm hoping that you said that it was our methane, CH4. What is it that's different? Well, it's the only one of these four different compounds, these four different substances, that cannot be reduced. It is the simplest, the most pure. We give that a name. We call that the empirical formula. Now, the empirical formula, and as with anything, I have a mnemonic, I have a way of remembering this. The empirical formula is the simplest formula for the compound. It is the smallest ratio of atoms, or it is the most reduced, simplest, the most reduced form. And I think empirical, you guys know me at this point. I think of the Empire. I know it's kind of silly, but Star Wars. Dun 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 dun. You think of the Death Star, the bad guys in Star Wars. The Death Star is the simplest form of evil. It is the Death Star. It is the most reduced form. It is a device for death, aka the Death Star. You don't see couches in the hallways. All the hallways are nice and clear. Just the stormtroopers, their weapons, and this giant tool for destruction. The empirical formula is the simplest, the most reduced, the purest form, if you will. So, all right, take a look at these four for me. Which of these four would be considered an empirical formula? Which one cannot be reduced? Well, I guess there could be more than one. Of the four choices, our first one cannot reduce a 3. That is a prime number. And the last one, cannot reduce to 1. Magnesium is already reduced to 1, cannot be reduced further. These other two, you'll notice, the sodium, sulfur, and oxygen here could all be reduced by a 2. Our mercury and nitrate could also be reduced by a 2. You could reduce both the Hg2 and the NO3 2. So empirical formula is the most reduced, the simplest form of our compound. So our goal is now that we know, okay, we can go from compound to percents. We're going to go backwards from percents to the compounds. To do that, we've got a set of steps, a way to get from point A to point B. And our first step is to start with the known mass. You need to know something. And this is an analytical tool. In the lab, you would have a device called a mass spectrometer, that would actually tell you what mass of each element is in the compound. So you'd start with that known mass. You'd have to do some sort of a measurement. You'd have to do some sort of tool, some way to measure the amount. Now here, I apologize, that got cut off by the video a little bit. That says start. So you're starting with the known mass for each element. And you're going to start by changing those grams into moles, because not every element has the same mass. For example, hydrogen. Hydrogen is the lightest of all of our elements. Oxygen is heavier. Lead is much, much heavier. So we can't compare them by using their masses. We have to change them into something else. We're going to change them into moles. To do that, we use our average atomic mass from the periodic table. Then we go ahead and we divide each element by the lowest mole value. So what we're going to do is we're going to set up a ratio, a proportion. Now that we've changed them from grams to moles, then we can start to compare them. Right? So once we set them up, we compare them, we're going to divide all of them by the lowest mole value. If the answer is a whole number, we're done. We're going to use those numbers for the formula. However, if the answer is not a whole number, if it's a decimal, we're going to double all of the atoms in our compound and use those to write the empirical formula. Now I know there's a lot here, so let's simplify. Let's condense it down a little bit, and something a little easier to use. All right, and again, I like to think of ways to help me remember, so here's what I'm going to use. Now, if you'd like to pause it, get this down real quick, feel free. But if you want the shorter version, here's a shorter version. Percent to mass, mass to moles, divide by small, multiply till whole. These are kind of your 4 steps. All right, if you want to help remember it, I find putting it to music helps significantly. So percent to mass, mass to moles, divide by small, multiply till whole. Again, percent to mass, mass to moles, divide by small, multiply till whole. You follow these 4 steps, you can get from the percents or the mass back to any empirical formula, the most reduced form. So let's take a look. Let's see what this would look like with an example problem. So let's go ahead and take a look at this one. So in a compound, the compound is analyzed. And in that compound, there are 4.364 grams of phosphorus and 5.63 grams of oxygen. We now need to determine the empirical formula of the compound. Well, okay. We've got our 4 steps. Percent to mass, step 1. Well, here's the cool part. We're already in mass. We've got that first step taken care of. Let's go ahead and write our 2 masses out to be able to work with them. Our next step, mass to moles. All right, I apologize for the sound here, but I do want to write on the screen so you can see what this would look like. We're going to change both of these into moles. So we're going to use the periodic table. Head on over to the periodic table, find the average atomic mass for phosphorus. You'll find that it has a molar mass of 30.97 grams for every 1 mole. Your grams are going to cancel. This will get you into moles of phosphorus. You do this calculation, you will find that you have 0.1409 moles of phosphorus. Do the same for your oxygen. Molar mass of oxygen from the periodic table, average atomic mass of 16.00 grams for every 1 mole. You divide those two, and you find that you have mole value of 0.3523. Okay? We're looking for a compound. We're trying to write a formula. Well, we know that in our formula we've got 2 pieces. We've got a phosphorus and an oxygen. Well, okay, that part's pretty easy. The part we're missing are the subscripts. We're missing the number of each element as it applies to the whole. Well, bummer. We can't compare the masses to masses because phosphorus and oxygen do not have the same molar mass. Each atom has a different mass. So we got to start by getting rid of the mass part. So now we're into moles. Now we can compare them. Alright, so what we just said is that for every 0.1409 moles of phosphorus, we have 0.3523 moles of oxygen. Oh, cool. Gee, thanks, Mr. Jorgensen. That ratio is super lame. Right? This is an ugly ratio. This ratio is ugly. This ratio is ugly. Let's clean it up. Right? Our first step, we didn't have to worry about percent to mass. That was done. Second step, mass to moles. We just did that. Third step, divide by small. Well, which number is smaller here? The 0.1409 or the 0.3523? Well, the smaller value is definitely going to be our phosphorus. So we're going to divide both of them by that 0.1409 moles. When you take a number divided by itself, you get, please say, somebody said 1. Please tell me you said so. You said 1. I know you said 1. I heard you. All right, so we're going to get 1 for the first. When you take the second set of numbers and divide, you come out with a value of 2.5. That ratio is much nicer. What this tells us is that for every 1 phosphorus, we have 2.5 oxygen. Oh, well, we can't have half of an oxygen. That does not work. So we need some way to keep the ratio the same, the proportion between these two the same, while at the same time making it a whole number. Wait, percent to mass, mass to moles, divide by small, multiply till whole. We're going to multiply both of these by 2. When we do that, we find a new ratio of 2 to 5. This is your ratio of atoms in your compound. This tells us that in order for this compound to be stable, we must have 2 phosphorus for every 5 oxygen. All right. Oh, and bonus points. What would you call this? P2O5. Hopefully you would call this diphosphorus pentoxide. Right? So all we've got now is a new set of tools, a new set of steps to help us go from percent to mass. Then mass to moles, divided by small, multiplied by whole. So really from percentages back to the subscripts, back to the stable, most reduced compound. Well, cool. Now that we've seen one here, let's take a look at one from your homeworks. If you'd be so kind, go ahead and pull out that homework sheet for me. Let's take a look at that new. All right, let's go ahead and take a look at number 3 here. Now on number 3, we've got 2 elements. We've got iodine and we have oxygen. So we know our compound is going to be made up of I and O. The part we don't know is how many I's and how many O's. That's okay. We've got percentages. We can change that into our subscripts. Remember your 4 steps. Percent to mass, mass to moles, divide by small, multiply till whole. Now we haven't done that first step before, that percent to mass. But here's the good news. It is my favorite step ever. Because what if we were to assume, okay, we measured out some of this compound with iodine and oxygen. Let's say we measured out exactly 100 grams. What would that mean for us? If we measured out exactly 100 grams, how many grams of it would be iodine? That's right. It'd be 76 grams. So the first step, easiest chemistry step ever. Grams, percent, to grams. All we gotta do is cross out the percent and put in our grams. So percent to mass, cross out the percent, put in grams. Next step, mass to moles. So we know we have 76 grams of the iodine, and we know we have 24 grams of the oxygen. To change from mass to moles, we divide by the molar mass. So let's go ahead and set it up. Iodine we put over 1. We go to the periodic table, find the average atomic mass for iodine, which we find to be 126.90 grams per every 1 mole. When we divide those, we end up getting 0.60 moles. We do the same thing for the oxygen. Find its average atomic mass. Average atomic mass of oxygen is 16.00 grams. Excuse me my writing here. For every 1 mole. When we divide those, we find we have 1.5 moles of oxygen. Now we can compare them. We've changed from the mass into moles. Now they're in the same plane. Now we can compare them without the mass aspect in there. Now we set up a proportion. So for every 0.60 moles of iodine, we have 1.5 moles of oxygen. So percent to mass, done. Mass to moles, done. Divide by small. So we're going to divide both of these by the smallest value. In this case, it would be 0.60 moles. A number divided by itself will always give you 1. 1.5 divided by 0.6 gives us 2.5. So divide by small. Last step, multiply till whole. All right. We do not have a whole ratio here. We've got 1 to 2.5. So we're going to make it multiply both sides by 2, multiply to the whole. We become a ratio of 2 to 5. The ratio is intact. 1 to 2.5 is the same as 2 to 5, but now we have whole numbers. These numbers become our subscripts. I2O5. If we had to name this, we'd call this diiodine pentaoxide. Okay. For tomorrow, please work on this particular homework item. You are more than welcome to work together with a partner. If you have questions, please email me. Best of luck. Hope it goes well.